They come from the Institute of Applied Physics from Florence. Ahora es el profesor Gualtiero Nunzi Conti, ¿sí? My pronunciation is not very good, the Italian names. Y el profesor Fulvio Rattio, ambos, como les dije, del Instituto de Física Aplicada Nelo Carrara, de Florencia, Italia. Nos van a brindar charlas el día de hoy con temas interesantes. En primer lugar tenemos al profesor Conti con su tema de Coupling Light into Ultra High Q Optical Resonator. Y después, con una segunda parte del seminario, tendremos la charla titulada Integration of Plasmonic Contrast Agent into Multifunctional Devices. Entonces, pues cedo la palabra a our first talk. Please.
Okay. Okay, thank you for the introduction, and I'm very glad to be here. So I will present results that are related to our joint project. Specifically, I will speak about how you couple light to high-Q whispering gallery mode resonators, and also give some demonstration. So the outline, some basics of micro-optical resonators. I will describe light coupling schemes to these resonators, and also what I call coupling regime analysis. So it's a way in which you can assess what type of coupling you are having. And then I will show some example of what we did by coupling light with fibers and by coupling light with integrated waveguides. So the basic concept is that of an optical resonator. So light is confined in a closed path by a mirror, and can be a linear structure, can be a ring like here, so you have multiple refraction, or can be like in this spherical structure, you can have with the electrics total internal reflection and modes that propagates close to the equator. And then you have, of course, one of the mirror has to be partially transmitting in order to couple light and to extract light from it. And at specific wavelength you will have interference. So what we have been working with in terms of whispering gallery mode resonators, we have been working with microspheres made out from a silica fiber, just melting the tip of a silica fiber. We are also using doped glass in order to have some laser emissions, for instance. We are working with millimeter-sized discs made in crystalline material that can have very high Q factor. And here are what we are working with you, so microbubble resonators. This is a capillary, and here through basically putting some pressure in it and partially melting, we end up with bubble. So the nice part of this type of structure is that basically you can have the resonantly guided light, like here with multiple reflection, and you can have very low losses, so very high Q, and also you can confine quite strongly basically the light. So at the end you have small volume, high Q factors, you have high circulating power densities, and so you can basically do some studies, some investigation, fundamental processes in linear or in quantum optics, but you can also use these tools for application like photonics and sensing. So this is quite somehow annoying, but of course you have to know that this is just the electrical sphere, so you can apply Maxwell equation and solve for basically the modes of the structure, which are basically described by spherical Bessel function in the radial direction here. And in this polar direction you have spherical harmonics, and then you have sinusoidal behavior along the equator. And you can basically identify with what you call mode numbers the type of mode that you are analyzing. So what I want to stress is that, of course, then it's by applying the boundary condition that you end up finding the resonance position. So where you actually have the wavelength at which you have the resonances. And as in all cavity, you can define a free spectral range, which is basically related to, as in all type of Fabry-Perot cavity, to the inverse of the optical path. And interestingly, these resonators, we say spherical but are spheroidal, so typically you have some so-called degeneracy, meaning that when you don't have a perfect spheres, you have another free spectral range which you can define depending on the eccentricity of the resonator, and I will show you that this can be useful from some applications. And then you can define a propagation constant as in an optical waveguide, which is basically the wave number projected onto the equator. So, as I was saying, coupling light, what does it mean? It means that you need a coupling tool to inject light into this high-Q cavity, and basically you need evanescent field coupling to optimize the coupling, and phase matching and mode matching and overlap at the same time. And you can go, one way you can go with is that of fiber taper. So it's a fiber where you have here a very narrow waist, let's say between 1 micron and 4 microns, and you can couple, this is the taper, to your resonator, your spherical resonator. Another option is that of prism. Here we have been using prism coupled to millimeter-sized discs. It's here. It's not that visible, but anyway, this is a type of free space coupling. Light is coming from here, couple, and then goes back through the prism on the other side. Integrated waveguides. This is an example. Here is a lithium niobate waveguide coupled to a lithium niobate millimeter-sized disc. And this is another option. Basically, it's a type of hybrid solution in which you have angle polished fiber. And this is another case, another type of approach we have been using. We can classify somehow this structure depending on how couplers and resonators are. For instance, here we have both a micro-optical resonator, which is the sphere, and a micro-optical taper. So here it's the same. We have a micro-optical coupler, which is the prism, and a micro-optical resonator, which is the disc. Or you can have a fully integrated structure in which the resonator is integrated. This is a disc in silicon nitrate, and you can also have the coupling structure which is integrated. Or you can have what I call hybrid structure, in which you have, for instance, here an integrated whispering gallery mode resonators. This is basically silica toroid, and you can couple with a micro-optical device like a tapered fiber, the light. And finally, the other type of hybrid structure in which you have a micro-optical resonator and an integrated waveguide. So you can classify in this type of structure. Now I will go briefly through simple analysis of the coupling of this structure, in which what I want to stress at the end is that in order to assess the coupling regime of this structure, you need to use a type of approach which is called cavity ring down spectroscopy, which allows you to unambiguously define the coupling condition. So this is the simple case. You have a laser source, you have your waveguide, the detector, this is the resonator, this is the coupling region, and part of the light is coupled to the resonator, part is transmitted, and then you have the reciprocal situation. From the resonator, part is coupled and part is transmitted. So by doing some assumption, only one guided mode in your coupler and only one whispering gallery mode excited, and also by assuming that all the light is either coupled to the resonator or transmitted, so no losses, you can end up with this type of formalism, which is quite simple, in which you relate basically the power on the right side in the fiber and in the resonator to what you have on the left side. So G output and U2 with the input through this matrix where there are the coefficient transmission and coupling. And so you end up with some information, the power in the cavity, and here is plotted. And so in this case you have an enhancement of 18 in terms of power into the cavity. And typically the quasi-Lorentzian shape you can get from this formula. And this is by doing a slow scan in wavelength of the resonance of the cavity. And here you plot, this is the equation that relates the power and the phase, if you don't take the square, to all the parameter of the cavity, and you end up in transmission with the well-known quasi-Lorentzian shape. And here in red, it's shown actually the phase shift that you undergo when you cross the resonance. The point here, okay, this is the so-called lifetime formalism. Basically, you introduce a coefficient, a time coefficient. Tau 0 takes into account the intrinsic losses, so it's related to the intrinsic losses of the cavity. And then the coupling, the inverse of the coupling, you can also define as a lifetime. So it's a simpler way to rewrite the previous equation using this coefficient. And then by comparing basically in this region the coupling coefficient with the intrinsic losses, we end up with, let's say, 3 different areas here where the coupling is smaller than the round trip loss of the cavity, in which you have the undercoupling regime. Then on the other side, when the coupling is stronger than the losses, you are in the so-called overcoupling regime. And here, where they are equal, you have the condition of critical coupling, in which basically you don't see light transmitted through your taper. Here is different region where you have gaining material into the cavity, but at the moment we are not interested. So basically, you can see that by this process of slow scanning in wavelength, you cannot really access these 2 coefficients and so assess the coupling regime of the cavity because of the symmetry of TE and T0 in this equation. So here are 2 different cases in which, for instance, you have 2 very different cavity build-up factor, but you can say in which condition you are because the blue actually perfectly overlap with the red case, and they are totally undistinguishable. So the idea is that you make a type of faster scanning, meaning that you basically cross your resonance in a time interval that is comparable with the cavity lifetime. And then with this type of approach, you have to end up with a different formalism, which is basically in these equations. Again, anyway, what you are interested in is the output here, this equation, versus what you have at the input. And by putting together this equation, this is quite long formalism, but what is important to notice is, okay, this function here is symmetrical, tau 0 and tau e are symmetrical, but then this function that tells you the transmission is not symmetrical anymore, and so, I mean, tau e and tau 0 are not symmetrically present in this equation. So what you end up with is that if you make this fast scanning, you end up with different profile depending on the case in which you are in the undercouple or overcouple regime. So through a fitting procedure of the signal, you can say in which type of regime you are with your cavity. So basically what I'm presenting here has been the thesis of one of my students that did this quite recently, and to what was in the literature, which is what I just described. He added the case of a second port in which you can basically extract light from your cavity, so the dual port configuration. Here you have the input and the transmitted light, but then you have another waveguide that can extract light from another point. And there are a number of applications like filtering, if you want to make nonlinear switches, for optoelectronic oscillator, in which you need this type of configuration. And also you can qualitatively understand that if you have, for instance, a frequency conversion inside here, so you generate new wavelengths through a nonlinear effect or through laser oscillation if you have a doped material, by extracting light here, you avoid a residual pump that is on this side here. So for a number of applications, really being able to collect the light from another waveguide is useful. So what we wanted to do is to repeat the same type of analysis for this dual port. I won't go deeper in this, but the point is that what we are doing, why we want to access this coupling efficiency, is the fact that when you couple this kind of structure with a tape or with a waveguide, it's really something you can say. It's not like if you have a classical fiber ring in which you put a coupler of known characteristics. Here really is something you have to assess experimentally. So not going deep, I can say anyway that you have a similar matrix formalism, but you have now two matrices. We monitor both what happens here at the output of the input waveguide through this fast detector here, but also what happens here through the light that is collected from this other port. And what matters here is basically that, again, if you make a stationary scan, a slow scan, you end up with symmetrical situations for these three parameters. Now we have three parameters: the coupling of the first coupler, the coupling of the second coupler, and then the losses of the cavity. Again, you cannot see which type of regime you are in. So you will have the same, exactly the same shape both at the transmission port and at the drop channel for two different cases in which, again, for instance, the cavity build-up factor is very different, so 32 and 12. So this cavity is really loaded, has a lot of energy inside this, so there is a factor of almost 3 lower. So basically, we do the same, and we do an analysis in the time domain and with a dynamic regime, and we can observe that solving this equation, you end up with not symmetric presence of this term in this equation. So you can calculate from one of it the coupling efficiency of the upper channel, and from the second basically the coupling efficiency of the drop channel, and then also the intrinsic value of let's say the intrinsic lifetime of the cavity. And as you can see here, this is the cavity ring down at the through port, and this is the cavity ring down at the drop port. So basically this was the result of this thesis, which was then applied to the case of a high Q resonator. For instance, this one, we have the input and the output port. Here you see the cavity ring down measurement at the through port, and here at the drop port. And you can assess the coefficient. For instance, this is the coupling efficiency of the upper port, which is in the order of 10 to the minus 5. As I say, it's really low. It's very small percentage. Here at the drop port, and then you can also assess the losses in the cavity. So the intrinsic Q factor, you see it's almost 10 to the 9. These are state-of-the-art value, quite high. And also the finesses of the order of 10 to the 5. So I will now go to because I think we are already like 20 minutes. So just saying that basically what we also have by having this type of coupling is that by changing the gap between the fiber or the waveguide and the resonator, we can tune the transmission of our mirror, let's say. So this is an important feature of our structure. And this is the terms that basically tells us how you can calculate the coupling coefficient. Basically, it's related to an overlap between the field in the waveguide and the field in the resonator. And then you have also to take into account the phase difference, so the index has to be matched. Okay. So example of fiber coupling. I always say that a fiber taper is the ideal coupler. Actually, it was not me that said this, because basically it is easy to fabricate, and being a type of biconical shape, basically you can tune both the evanescent field. You can see here how the amount of field strongly depend outside the fiber, outside the core, strongly depend on the taper diameter. And also how the effective index can be changed within a large range depending on the size. So it's like a tunable coupler itself. And so where we apply this, for instance, one we did to generate the harmonic in a silica microsphere. Of course, you know that having high circulating intensity inside a whispering gallery mode resonator is not a condition sufficient to have a type of parametric third order conversion, because we need to fulfill energy conservation, phase, and mode match condition. This basically translates into selecting a certain size for the cavity when you want to have basically the energy conservation and the right whispering gallery mode to have basically phase and mode matching. And what we did, we selected the right mode, but to excite that mode, we need this type of coupling device, so a fiber taper, because we could select high radial mode simply by moving the taper from the equator to a higher order mode. You see here, you see two spots, two green spots. This is the third harmonic that is excited by exciting this higher order polar mode. I have not shown you how they look like, but basically they have two peaks symmetrically placed versus the equator. And so basically it's the demonstration that we could really excite those modes, and we could have quite an efficient process. We had, this is the typical, of course, the cubic dependency as expected for the third harmonic, so it's about 3 the slope, and with 80 milliwatt, of course this is the launch power, we could get about 1 milliwatt of third harmonic collecting the scattering light, and through the fiber it was 1 order of magnitude lower, but still it was quite an efficient process. Again, this is because we could couple the right whispering gallery mode. Another example of useful of how it is important the way you couple light is that, for instance, of generating stimulated Brillouin scattering in a microbubble resonator. Here is the scheme of this non-parametric nonlinear effect, or the nonlinear effect. And what we know is that in silica, the let's say the Brillouin level is about 10 gigahertz apart from the pump, but it's a very narrow gain bandwidth, which translates into the fact that you would need an extreme precision in making your resonator, which is not possible. And so how we demonstrate this stimulated, actually cascaded Brillouin scattering? We used the fact that you can have eccentrical, like strongly eccentrical cavity like this bubble that are not spherical. I recall you that if they are not spherical, they have a number of additional modes. They have just not one cone, but there are additional smaller one. And so basically by exciting those modes, which you can do by moving the fiber in the right position, we were able to obtain Brillouin scattering in cascaded actually. So here you have different order, and actually the even are more enhanced, sometimes the odd is much lower. But anyway, we could show that by exciting the proper mode with our taper, we could get even in this structure, which has no possibility of being done with such a precision, we could obtain this. This is what we are working on. So it's the idea of the project. Basically, it's to use this bubble resonator board for the microfluidics, and here we have metallic nanoparticles that are excite, so there are photoacoustic waves that basically produce oscillation into our bubble that can be read simply by using a coupled fiber, because when the wave hits the resonator, it changes the resonance position by changing the index or the size, and so you end up with a shift, and by using your laser at a certain wavelength, you can translate this shift into a change in the power. And the final thing, I will say some word about using integrated waveguides, because this was our background. We were coming from integrated optics, so we were making waveguide in glass, and long time ago, and lithium niobate. So the different from the fiber, the point here is that if you want to make a real device, integrated waveguide is really robust and very stable. And you can use a wide variety of materials, glass, silicone, polymer, and because you have a number of options in terms of index as compared with the silica fiber, which has that one. And so what we did basically in our case, this is the other important thing, mode matching with the whispering gallery mode is not needed. So what we have been doing with integrated waveguide couplers, there was a first experiment we did a long time ago with the group of Professor Wilkinson at the ORC in Southampton, is to couple light to a glass, BK7 glass sphere from an ion exchange, which was the technique we were using to make waveguide, made in the same BK7 glass. And we could excite the modes. We were using to control this gap and heavy stability a low index Teflon, so low index material, in order to control somehow the separation between the waveguide and the whispering gallery mode. And then we work with, as I said, with lithium niobate, because basically we demonstrate that we can couple light from a lithium niobate waveguide to a lithium niobate disc. And of course this was very important basically for optoelectronic oscillators because of the optoelectronic properties of lithium niobate. But we could demonstrate coupling from this proton exchange or titanium exchange, if we want both polarization, waveguide into ICAT lithium niobate discs. And here is an example of measurement of the same resonance made by a slow scanning and by a fast scanning. But you end up, of course, with the same tube. Here you can also assess the coupling condition. This is the difference. Final results we obtained with polymeric material. We wanted to couple light from, let's say, polymer waveguide into a self-assembled microbubble resonator. This is basically made on a fiber on which this type of SO2 polymer is basically self-assembled. And well, here we could demonstrate coupling, and of course we could demonstrate that where the absorption is much lower in SU8 at 770 nanometer, so we could get a larger, 1 order of magnitude larger Q factor. And so this was meant also with the idea of being able to fabricate a type of multiplexing in which you can easily fabricate a waveguide, polymer waveguide, and also this self-assembled polymer resonator. And finally, we have been working a lot on coating of these spheres, because basically you can think that if you want to assess the property of some material, you can use the spherical structure of your silica, and then you can coat it. So basically, it means that you add the functionality of the coating material to the properties of this IQ resonator. And we have been working with all gel glass, with polymers, with amorphous silicon. And in any case, here it was really critical to demonstrate that we were coupling the coated part and not the inside by tunneling, which has been reported sometimes, showing that if you want to use the property of the material, you need to couple light in the material. And so we develop a system, which I'm not described here, to demonstrate that you are actually coupling light into the coating. And we did this by using simply a rich SU8 polymer waveguide, and demonstrating that planar coupling could happen only in coating that had that were thick enough to have one mode inside the coating itself. So I hope, yes, I mean, I try to describe a little bit of theoretical things at the beginning, and then just to summarize what we have been doing, and of course also because if there is any topic we can work together, that would be, of course, interesting for future collaboration. So stressing, okay, the work of this Gabriele Fugenti on cavity and down spectroscopy, also in the double port configuration, which was able to assess the coupling conditions and the coupling regimes. And then I present result on parametric and non-parametric process in fiber coupled silica-based resonator, results on coupling lithium niobate disc with lithium niobate waveguide, and finally, more recent result on polymer-based resonators. Of course, our target is this within this project, so the optical detection of photoacoustic emission from metallic nanoparticle using microbubble resonator. Here, a long list of people, especially Gabriele, that did the work, thesis work, and he will be back working with me next year. So thank you very much.
Should we continue with the next talk, or it's time for some couple of questions?
I have a question. How you prepare your microspheres? In an artisanal way, or you have a machine that...
Okay, so I don't think we have a machine actually, and okay, there are different approaches how you melt. You can melt by CO2 laser, and this is a way you can control quite nicely. You can melt with a flame, and you can melt with arc discharge. So we were using arc discharge, and this because of our, let's say, background and using fiber splicer. And basically here is what we implemented. Okay, it's here. So this is also the same we are using for making the bubble. So it's basically, these are 4 electrodes that generate a plasma here. The way we have then a type of control with Arduino to select the time of this plasma discharge, and also the intensity, of course, the current. So there are some parameters that can be adjusted Still, we are not getting always the same result, especially in terms of thickness of this wall, which is important. But anyway, they are quite. It's a multiple step, so we do. It's not just one shot. We need to do it gradually while pressurizing the. So it's semi-artisanal. I would say it's even the polishing is the same. It's done quite in a homemade system.
Some other questions? Okay.
Yeah. I was wondering, this critical coupling theory is very closely related to coherent perfect absorption as well. If you tune, especially in the two-port configuration, if you tune well the absorption coefficient with respect to all the phases and all the parameters, then you can enter also this kind of physics. Have you ever?
You mean by changing the absorption in this case?
If you tune correctly the absorption and you are in the critical coupling, then you can absorb all the light in your resonator,
Yes.
and then you tune transmission, thing
Yes.
that works in this direction as well. Have you ever worked on that?
No, not really on this specific topic. So for us, it was important to be in the critical coupling condition and to be able to assess that because we wanted maximum power in the cavity to enhance nonlinear effects, because we have been working with those basically.
So when you use the two-port configuration, you inject in one and you read in the other one. You don't inject in the two at the same time.
No.
You never tried?
Just injecting one, collecting the other, and typically you need symmetrical coupling, and to get the most to get all the power at the second port. And you have also to play with the absorption of the material, with the losses of the material. They need to be, of course, quite low. Of course. Yeah.
And the other thing was, when you coated the sphere with metal and you approach the fiber, did you excite any gap surface plasmopolarity on there or not?
Okay, in this case, we are always working with the electric coatings. So we are thinking, we have been actually also investigating some feature, but you spoil a lot so far. We were putting some silver ions through some technique, but the Q factor is spoiled too much so far. But anyway, what we have been working with is basically sol gel, active sol gel, like this is silica hafnia, doped with erbium, and polymers with some dye or some fluorescent aptamer. This is for sensing, and amorphous silicon for, again, nonlinear effect and so on. So not with metals.
Okay.
It's okay. So next.